in this very nice conference. It's always a pleasure to be here. I'm going to talk about an aggregation model, a growing process on ZD, and everything is joined to work with vedadas. So let me start defining the model. Take ZD and start with a collection of particles. Very simple. Take each side, each vertex of ZD, and you put a particle there with probability mu, and no particle with probability 1 minus mu. And this is the set of red vertices here. So we have at most one vertex per side. And these red guys will evolve as the exclusion process. So this means that each such particle is doing continuous time, simple random walk on ZD, independently of the other particles, but with the exclusion rules. So this means that a particle always moves to uniformly chosen neighbors, but if a particle tries to jump on top of another particle, then the jump is suppressed and the particle stays in place. On top of this picture, I put at time 0 an aggregate, which I'm going to represent by black balls. And this is just going to be a subset of ZD, and it starts containing only the origin. So I have only the black ball at the origin. And this aggregate doesn't move, so the black balls will always stay there. But it grows, and it grows whenever one of the red particles expresses a wish to jump on top of a site that is occupied by the aggregate, as in that case. And in that moment, the jump is suppressed, and that particle becomes part of the aggregate. So in this way, the aggregate is growing by gluing particles that tries to jump on top of it. And whenever a particle becomes parts of the aggregate, it will never jump anymore. So now it's a black particle, so it stays there, it stays fixed. Okay? And you are interested in looking at how this black set grows over time. That's the goal. So this process has been studied mostly in the physics literature, where people tend to attribute its introduction to Foss from 1984, which introduced this process that I call multi-particle diffusion limit aggregation as a more realistic version of another process that's called diffusion limit aggregation without the M. And this process is got very popular, and it was introduced by Witten and Sander in 1981. Let me just define this quickly. It's the same kind of process. You have an aggregate starting at the origin, but you don't have these red particles anymore. Instead, what you have is you start with one particle from infinity, and you can make formal sense of that, and let this particle do a simple random walk until it eventually tries to jump at the origin, and at that time, that particle becomes part of the aggregate, and then another particle is released from infinity. And you do it again, again, and again, over and over again. So you add one particle at a time. Foss said that this is not very realistic, because in physical systems, usually you have a density of particles starting already in the system. Particles are not going from infinity. And that's why he introduced the multi-particle version of it. What Foss missed is that MDLA was introduced before by Rosenstock and Marquardt in 1980, even before DLA was introduced. And they introduced MDLA because they were interested in a model, that they observed in photography. And the irony goes that actually Witten and Sander, in 1981, they introduced DLA as a simplified model of the model of Rosenstock and Marquardt in 1980, because they couldn't simulate this MDLA. They want to simulate it with the computers at those times. So handling multiple particles was too much to ask for, so they was adding one at a time. And even more interesting that Witten and Sander, of course, they cite this paper, and Foss just missed that. But he reinvented it, so that's okay. So and why they were actually interested in this? So the first reason, and this is really true, is because they produce beautiful pictures. And actually, Sander, in 2001, said that the only reason he really defined this model is because they had just bought a new computer of those times, and they wanted to produce nice pictures out of it. So that was really the reason. And why is this beautiful? So let me show you a picture. I hope now everything still works here. Let's see. Oh, is it? Oh, yeah. So that's a simulation by Vincent Farah of DLA, the one without the M. I hope this, okay, without the M. And you see the growing, I'm just showing you the aggregate, and it produces quite of intricate behavior. It has these branches going along the axis, and they produce these very delicate arms that looks like fractal-like. And it's easy to understand why these arms are robust once they exist, because once you produce, for example, this arm and say this arm, it's much more difficult for a particle coming from infinity to enter, pass through this small opening and aggregate inside. And the thing that fascinates people in general is that this process is quite, you see these arms at all scales. So if I zoom in, you see these arms at all scales growing. Okay? So that's the beautiful pictures that Witten and Sanders were interested in. But that's not only the only reason, but they can observe that some systems in nature have such type of behavior. Now, I'm not sure this will work, but let's try our best. OK, I can still see it. You can barely see it. But believe me, there is a square here made of acrylic. And acrylic is a very good insulator. And what they did is they take this square and they bombard it with electrons. If you put too many electrons here, it breaks the insulating properties of the material. What they did is they just put enough electrons up to the threshold at which it would break. So it's right before breaking. And then they do something very subtle. They take a hammer and a nail, and they make a fracture at the top of the acrylic. And at that point, the threshold for breaking down the acrylic decreases. So the density of electrons is just too high. It breaks down the acrylic, generates energy, which causes neighborings to break down the acrylic, and so on and so forth, causing a cascade. And then don't blink for the next 10 seconds, because everything happens very fast. So I'm just going to puncture this, and then that's it. So what you see is that the picture that forms has this similar, or at least resembles these fractal-like arms that were producing with the simulation of DLA, for example. Okay? But still, they are more different, because DLA was just along the axis. Right here, you see a more dense set of arms. Okay? And this is not the only process that you see this kind of phenomenon. Let's stop this fun. For example, you can also see this phenomenon in electrodeposition when you break down the molecules of a liquid with electricity. You also see that the part of the liquid starts to deposit along the wire here, and you see they still form these branching fractal-like arms in the picture. And there are more and more examples of this. Also, if you want to burn a piece of wood, who would like to do that? But people do it, and you get also this kind of shape. Okay, so that was the main attraction. So there are very different types of systems, physical systems, and all producing this kind of fractal-like, beautiful pictures. And I know there are many others that are, for example, in fluid dynamics, there is Hellish-Shaw flows. And probably some of you know much more about this than me, and I would actually be happy to talk with you more, to learn more about these things if you are familiar with them. So let me jump here a bit. Okay, so what do I want to know? I want to know the shape of this growing set of these aggregates, and now I'm going to focus on MDLA. So we have all these multiple particles in the system. So that turns out to be a very difficult object to study. So let's look at a very particular question. In particular, how quickly does the aggregate grow? In particular, I want the question of, does the aggregate grow with positive speed? Which means that if I observe the process for time t, will the aggregate reach a vertex of distance t by that time or not? So that's the question I want to address. And let me say, previous work on this, there is a result by Harry Keston and Vlad Storavicius that they studied the one-dimensional case. And let me say that that's the only, really the only result in the mathematical literature about this before our work. And even physicists don't understand this model very well. So even if the physics literature, there is no consensus of what happens as the aggregate grows. So for dimension 1, they show that for any density of particles between 0 and 1, the aggregate does not have positive speed. It can only reach a vertex of distance root t by time t. And, okay, it's difficult to say that on camera, but I would say this is not a really difficult result to prove. Right? It's just one dimension. The aggregate has a very simple geometry. Very simple geometry. But I mean, it's still a fair good result, but it holds for any density, and so on. And then just have to point out that after our work, Harlan Sly got interested in this and worked on one dimension as well, and a slightly different version of the process that he could make sense of density bigger than 1, and there he could show positive speed, but I'm not going to concentrate much on this case. So let me say, because our work is mostly for dimensions 2 and higher, which was completely non-understood, and there could be different regimes in terms of low density and high density of particles, which was not showing in one dimension. And to illustrate a bit this, let me consider the extreme case of density 1. So consider density 1, so I'm not drawing here, but to see all these sides here, you should see a red ball representing a particle there. So they cannot move because there is particle everywhere. So the only thing that happens is that the only action happens when a particle tries to jump on top of the aggregate. And this happens, each particle tries to jump on top of the aggregate at rate 1. So what happens is the aggregate will grow by choosing one of these neighbors uniformly at random and just aggregating it. So what you see is really a process known as first passage percolation, more specifically the Eden model, where the growth of your process is just that each site at the boundary of the process, the external boundary of the process, is at rate 1 being aggregated to the process. And this process has a very different behavior than the one we saw in pictures. In particular, it does not have these arms. It's very bulky. It actually forms, it does have positive speed of growth. And actually, there is a shape theorem in the sense that if I take all the sides here occupied by time t and scale it correctly by t, I get a deterministic set on ZD. And this set is actually a norm. It forms a ball according to this norm. So it's a bulky set, doesn't have these fractal-like arms. So mu equals to 1 is very different than the picture we saw for DLA. And the question is there a regime where if I have a high density of particles, I see something like FPP, like first passage percolation, bulky, and if I have a low density of particles, then I see something more like DLA because particles are coming from far away, so they could look like as coming from infinity. So that's the picture I would like to understand. So let me show you a couple of simulations. Let's start with high density. So this is a process. I'm just showing you the aggregate growing. That's high density of particles. So the density is just 0.45, but it already seems to produce a behavior like first passage percolation. First thing that you can see is that the aggregate grew very fast. Just start growing like a ball. It looks like a ball if you look from far away, but still you find that very delicate and very long empty regions that the aggregate will never aggregate. In particular, the aggregate has to aggregate. As it aggregates particle, it leaves. It has to go around regions where it doesn't find particles, and these regions form very long and delicate structures, and do not really look like, for example, vacant sets of IID percolation or anything like that. But it does look like FPP in the macroscopic scale.
These arms can reconnect, right?
These arms can reconnect, yes. Some of them do. And, but still, they form very long regions where that's left to be. Yeah, I'll get back to it, but yes, for high density, you find them finite. You get finite regions. On the other hand, if I do smaller density, and the density is just 0.23, just trying to speed up the simulation. So the density is just 0.23, it was just half, I think about half of what we had before. And the first thing you see is that, well, first it's much slower, so it's taking much more time for the simulation to evolve. And you start seeing that you see much less of this bulky shape, and start seeing these growing arms, fractal-like arms like DLA, the picture for DLA was showing. So it seems like there is a different behavior here. For high dimensions, high density, you should see more or less like first passage percolation behavior. For low density, the simulation suggests you see something like DLA behavior, but still it's not clear whether this is just initial stages of your process, whether after a long time things will behave different, and that's where physicists also don't have a consensus about. Right, and just to conclude this very brief introduction, let me show you a picture of density 0.1, which takes just too long to simulate. So this picture took 1 month to produce. And it's like 0.1, and has, I don't know, maybe 8,000, I don't know how many, maybe 20,000 by 20,000. And you see this very similar behavior like DLA, but again, it's not clear. Let me zoom in, and you see behavior very similar to the picture of DLA, but again, it's not clear that this is just show initial stages of the process, or it's actually the behavior we should expect. So that's the very nice process. So let me say what we can actually prove about this. Okay, so our results are the following, that we show that there is a regime of positive speed of growth in dimensions 2 and higher. In particular, if the density of particle is large enough, larger than some value mu 0, then with positive speeds, the aggregate grows with positives. With positive probability, the aggregate grows with positive speed. So we can find, at least for large enough densities, that what we saw in the simulations, that this aggregate was growing very fast, does hold. And we can show a bit more than that. We can show that the aggregate has positive speed in all directions. And we can show what Hubert was commenting, that the vacant region is always composed of finite components. Particularly the aggregate, if I take the aggregate at time t, and I take all areas of the complement, all the finite components of the complement, by time t, this will contain a ball of radius ct. Okay? Yes? What?
If you look at the white region, does the density?
The white region will have a density 1 minus the density of particles.
Yes, so is the density. So the density of the aggregate is
mu. Yes. Yes. Yes.
So the surrounding area just leaves the neighbors?
No, you take the complement of the aggregate, take the finite components of this complement, and these are the surrounded areas. The areas that are disconnected from infinity by the aggregate. Okay?
But those areas still have density? No.
Those areas still have density.
But they don't have no longer any particles, right?
Yes, but you see, they don't have particles, but they form a dense set of ZD. That's the. Okay. Let me just say there is a star here, not by chance, that if you modify the argument of Alan's lie for 1 dimension, you can boost this to an almost sure result. So you get that the aggregate has positive speed with probability 1 when the density is high. But his technique is very 1 dimension. It can, even if you modify it, you can just prove this. You don't get that this occurs almost surely. You just get, you have positive speed along the axial direction. It's very strange, but that's what to come out of it. And then the main question, main open problem here is what happened at low density. And this, we have no result about this, and even people have different beliefs. And my current belief, which also changes over time, but current belief is that there is positive speed for all densities. Okay? So that's the argument. Well, I would be happy to talk more about this offline if you're interested in it. So let me rush a bit. How long do I still have? Like five minutes, okay. So let me just rush a bit. I just want to give you an idea on how to prove this result, just because the proof comes by introducing a different process, which is very interesting in my opinion. So let me just skip here. Actually, I don't need this slide. Here. I introduce with a simulation. So let's introduce a different process. So forget about MDLA. So I have another process which will be a first passage percolation, but with two types. Black, which starts from the origin, and red, which starts from IID Bernoulli random variable. So each site is occupied by red with some fixed probability P, or not occupied by red with probability 1 minus P. And the origin is always black. And the process starts as follows. Only the black moves initially, and the black is just performing first passage percolation. So it's just aggregating the neighbors at rate 1. So it grows like this ball, but it grows until it touches a red, which became yellow, and you cannot see it, but just believe me, it's here. So anytime the black tries to occupy a site that's occupied by the red, the site becomes yellow, and this site starts evolving like a first passage percolation, but with a slower speed. So instead of spreading at rate 1, it spread at some rate smaller than 1. Right? So the picture we're going to see is something like this, and the process continues. And each site can only be occupied by either black or yellow or red, the second type. And you have a competition, because black is faster. So it tries to go around the yellow guys, but the yellow, there are many of them. So there is a trade-off between the density of the red seeds that will give rise to yellow clusters and the spread, the speed of spread of the black cluster. And the reason here is, remember that when the density is 1, the aggregate was growing like a first passage percolation. So what we can do is we can do a coupling between these two processes so that the aggregate will always contain the black set, the black cluster. It's like evolving like first passage percolation. And the yellow cluster they will contain the regions that will not be occupied by the aggregate. So the regions that the aggregate has to go around it. So that's the main, well, I won't have time to give all the details, but that's the idea by coupling these two processes. But this process in itself, I find it very interesting. There is this competition between the two types. And let me just quickly go here. So there are 3 possible regimes that you can imagine for this process. The first regime is what I call extinction, which means black stops evolving. Black will stop growing eventually, will be surrounded by yellow clusters, and will stop evolving. And this regime for sure happens just because I could take the density of the red seeds so big that it's bigger than the percolation probability, and it's bigger than the probability needed for the vacant set of percolation to have an infinite cluster. So the origin will always be initially surrounded by the red seeds, and won't be able to escape that region already. The other 2 regimes are not obvious whether they exist or not. The first is strong survival. Survival means that the black type survives, will continue to grow indefinitely, but strong survival means it grows by killing the yellow. So essentially it will surround and confine all the yellow clusters to finite clusters. Okay? And the other would be coexistent, which would be both colors would produce infinite clusters eventually. It's not clear whether these 2 occurs, but what we show is that the regime of strong survival occurs, and we show a stronger result. We show that for any speed of the type 2 cluster, any speed that's smaller than 1, smaller than the speed of type 1 cluster, than the black cluster, there is a density, P0, such that if the density of type 2 is smaller than this density, then type 1 survives with positive probability. So no matter how fast the yellow is, as long as it's lower than the black, there is a regime of survival for the black. And this is crucial for us to prove that the aggregate grows with positive speed at actually all dimensions. So let me just finish by quickly showing you simulation about this new process. We cannot show coexistence. That's a very interesting open problem. Let's do this. So this is the regime essentially that we show, which I'm just showing the black cluster here growing. If you want to show the yellow cluster, it's going to be like that. So you see the black cluster grows. So the speed of the yellow cluster is 0.7. And the initial density is tiny. I'm not sure if you can see. It's 0.027. That's the initial density of the red seeds. It's quite obvious that we would expect at this density that the black cursor will survive. But what is quite amazing is how big these regions get, even if the density of these red initial seeds are very small. And it gets very big. You see, they have a huge impact on the growth of the black eye. But still, this is a case of strong survival, since you see that the black cluster is surrounding eventually all the yellow clusters that grow. That's the regime we proved. And the other case that I want to show quickly is the case where the density, the speed of the yellow cluster is the same. It's also 0.7, like in the previous one. But I increased the density just a little bit. Now the density of the red seeds are 0.0305. And then what start to see a completely different picture. And you see very strange behaviors, like, look at this guy. He's just growing one arm, and it's surviving. I don't know why, but it does. And if I show you and if I show you the yellow cluster, it grows more or less like that. And you can find this. I mean, I can run even longer simulation. You find similar pictures of like single arms that manage to survive and at the end branch to other process. And it's difficult to say whether these arms will eventually all die out and we are in a regime of extinction, whether these arms will eventually find one another and in a regime of strong survival, or whether these arms will just keep growing and you are in a regime of coexistence. So this is a quite fascinating thing for me. And just to finish, I just want to say that we can show coexistence, this regime of coexistence, where both types produce infinite clusters, in a model of deterministic evolution. And I'm just going to leave you with a picture. If I can show the, yes. A model where now the growth of the black cluster and the growth of the yellow clusters are in discrete times, but different times. The black is faster than the yellow. Then we can find, and we can show that there is a regime where both processes survives. The yellow survives along the axis, and the black survives on the diagonal direction. So with this, I stop here. Thank you.